I'm Kristen, and this is problem 4 from exam number 3. So the problem is a negative fluorine atom with a charge of -E heads towards a region with a constant magnetic field of 0.08 Tesla at 400 meters per second pointing out of the page. The magnetic field region is a cube with each length being 10 centimeters. The ion enters the field region in the center of the side. Does it exit? If so, where does it exit? And what is its velocity as it exits? So here's a picture we drew. This is our fluorine atom going into the center of this side, and we see our magnetic field pointing out of the board by the dots, and then each side has a length of 10 centimeters. Maybe not drawn perfectly to scale, but just imagine, each of these are 10 centimeters. So
Hi, I'm Abe, and I'm part of the group, Extra Credit Project. So a good way to proceed with this problem is to see what we have. We have a mass, we have our charge, we have the B field, and we have velocity. So what we can do based on what we know is we can use the equation F equals QV cross B. Just seeing what we have, we know we can plug in some variables, but before we do that, we realize we have a mass. And mass isn't in QV cross B. So that gets you thinking, okay, maybe we can relate this to Newtonian physics, where F equals ma, right? And if F equals ma and F equals QV cross B, you can equate them both, and you get ma equals QV cross B, right? So now we've incorporated our mass. We have an acceleration, which we'll get to later. And we now want to see what direction our fluoride ion is actually going. So we'll do that with this cube drawn here, and in the problem it is given that this is a cube, and the B field is coming out, so it would be in the positive Z or a positive K hat direction, right, coming out. And we have this fluoride ion coming in. Now, the question is, well, how do you want this fluoride ion coming in? Well, you don't want it coming opposite of the magnetic field, which is the negative Z hat direction or the negative K hat direction, because the fluoride ion would just go straight through. If you do the math here, if you do Z cross Z, you would get 0, so it would just flow straight through. So the logical method that you would use is you would have the fluoride ion going perpendicular to the B field. And in doing that, you have the fluoride ion coming in from the bottom going in the positive Y, which would be the positive J hat direction. So now you know that it's coming at a velocity at the J hat direction. So we have V, J hat, and we already said that our B field goes in the positive K hat direction. So now we isolate our terms, we get J hat cross K hat, and we know from the right-hand rule that J hat cross K hat is I hat. We isolate our magnitudes, we have our direction, we relate it to Newtonian physics, and I'll leave it to Kristen to explain the rest.
Okay, so now we're left with mass times acceleration equals QVB I hat. But in order to find the velocity at which it exits and where it exits, we need to kind of elaborate on the acceleration here. So we know that the acceleration is going to be in a centripetal direction. And we know that because, refer to my diagram here. So using the right-hand rule, we use our thumb for the magnetic field. So our magnetic field is going to come out of the board like this. And then our velocity is going in the positive Y direction, positive J hat, so it's like this. And wherever your middle finger goes at that point is going to be your force. So there you can see that no matter where your velocity is, your force is always going to be perpendicular to that. And because the force is pulling the ion in this way, it turns into circular motion. So then we know from physics 1 that acceleration in a circle is v squared over r. So we can just plug that right into our equation. So we get mv squared over r equals qvb I hat. And this R is actually going to tell us where on this side, if it does exit, where it will exit, where the ion will exit, either over here or over here. So then just do some algebra. We take the mv squared over this side and then cancel out the v's. You get R equals mv over qb. And then once you plug in all of these terms, you're going to be able to find your direction and the magnitude for R.
Okay, so hey guys, I'm Rochile. So first, when we want to find the radius for this problem, we need to figure out the masses. Now the mass is given in AMU, but that's not going to work in our SI unit scale. So there is a conversion available in which 19 AMU, you would multiply that by 1.66 times 10 to the negative 27 kilograms to get the mass in kilograms, which we calculated here. Now, moving on is a little bit simpler because you know that you have the mass, which is this value, and then the velocity, which is given as 400 meters per second. And we know that the velocity is going to be consistent throughout the problem because it is in centrifugal acceleration. So the velocity is constant while the particle is moving in a circle. And then we have Q, which will be a negative 1.602 times 10 to the negative 19 coulombs. And this is because, remember, our charge is negative electron for the fluoride ion. And then we have the B field, which is given as 0.080 Tesla. So then we do the calculations, and we find out that the radius is negative 9.84 times 10 to the negative 4 meters. Going back to the scale of things, it's in the centimeter scale. So we would convert this to centimeters to get a negative 0.0984 centimeters. Now, we know from the beginning of the problem that the ion will enter in the center, which means that it will be in the 5 centimeter marks if you count this as 0 and this as 10. So knowing that it will be a negative value for the radius, it will turn in that direction and it will exit out this way. So we can actually draw that in here in the circular motion. And then this value here will be the negative 0.09 centimeters. So to figure out what distance that is, we do 5 subtracted by 0.09, and we get 4.9 centimeters is the where the particle will exit.
Cool.
Sounded good to me.